We really hope you enjoyed the lightning talks and that you got a chance to interact with other participants on the town, and that you joined the active break. That was really great. So I'll now let Alex present our second speaker.
Yeah, thanks, Laurence. It's my great honor to introduce Professor Megan Peters for this keynote talk. Dr. Peters received a PhD in computational cognitive neuroscience from UCLA, followed by a postdoc there as well. And she is, since last year, right, an assistant professor at the University of California, Irvine, Department of Cognitive Sciences, and also cooperating researcher in the Department of Decoded Neurofeedback at the Advanced Telecommunications Research Institute International in Kyoto, Japan. Megan's research aims to reveal how the brain represents and uses uncertainty and performs adaptive computations based on noisy, incomplete information. She specifically focuses on how these abilities support metacognitive evaluations of the quality of perceptual decisions and how these processes might relate to phenomenology and conscious awareness. And she uses an impressive panoply of methods to study all this: neuroimaging, computational modeling, machine learning, neural stimulation, and I think we'll get to see some of this in her talk. And last but not least, not only does she contribute to the progress in consciousness research, but she has been leading the efforts to create Neuromatch Academy, which I'm sure most of you are aware of. And this is, in my opinion, a tremendous contribution to neuroscience, and I would say to science in general, to make it more inclusive and accessible for all. And actually, I think the deadline for applications has been extended in the last few days. I'm not sure of this, but yeah, Professor Peters, we are very pleased to have you with us today, and the floor is yours.
Thank you so much, and I'm really pleased to be here. This is a great honor to be here with you all and to be talking to this group. So I'm grateful for the invitation. Thank you so much. And I'll also say that even though I'm not talking about Neuromatch Academy today, I want to highlight that it is definitely not just me or just a few people, that this is a huge heroic effort, including some of the folks here. So we're very pleased to have kind of the not only promoting global access to neuroscience education, but promoting global involvement in creating that access. And I think that that's just phenomenal, and I'm honored to be a part of that. So, but we're not talking about that today. Today, we're going to talk about consciousness. And so I hope that you guys will enjoy this talk, and then I'll be looking forward to your questions towards the end. Okay. So today I'm going to talk about how I hope that we can link metacognition and consciousness using computational models, and specifically how we can study consciousness scientifically using metacognition. But I wanted to start by talking a little bit about what I mean by consciousness when we're talking about this, and also to differentiate this from some of the more technical talks that might be going on during this symposium, and to show you that we're kind of getting into the philosophy realm a little bit, but that's kind of fun. So presumably all of you here in the audience are conscious. There's something that it's like to be you, to feel the feelings that you have, to see the light that's coming in through your eyes, to hear my voice right now, which is just sound waves coming in through your ears. And so what we mean by this is when we define consciousness in this way, it's not the difference between wakefulness and sleep, or awareness and coma, but more it's about the perceptual and emotional and memory experiences that you have, which have phenomenal character, for which there is something that it is like. And so one of the major thrusts in my research program is to try to understand how in the world this happens, and specifically to try to get at how this happens, not through theory alone, but through scientific inquiry. So there are a lot of different potential ways to solve this so-called hard problem, if any of you have read Chalmers recently or in the past 25 years. And these potential ways to solve the hard problem seem to be kind of all over the place. So we've got a lot of competing theories out there right now. So you might have heard of some of these. There's the global workspace theory, that information that gets into the global workspace that therefore is broadcast and becomes conscious. We have local recurrency theories that say that the local feedback within primary sensory cortices is both necessary and sufficient for the creation of phenomenal awareness. We have information integration theory, which says the more integrated information that you have, the more conscious you should be. We have quantum theories about how the quantum vibrations of microtubules lead to consciousness. And then we also have higher order theories saying that it is the second order representation that somehow is involved in the production of phenomenology. And there are many others, but a lot of these theories are kind of at different stages. They target different things. So there are efforts going on right now, like the adversarial collaboration project that's funded by the Templeton World Charity Foundation, that seeks to take two of these theories and kind of pit them against each other to see which one comes out on top. But the challenge in doing this is that some of these theories are really mathematical, but they're not necessarily as grounded in empirical data. And other theories are kind of the opposite. Others are also more philosophical and may not have obvious approaches for specific scientific inquiry. So the plethora of information and the diversity of the theories out there might lead you to think, you all in the audience, that maybe the hard problem of consciousness isn't ready to be tackled by science yet. And in fact, you might even find yourself asking, can consciousness even be studied scientifically at all? And I think the answer is yes, but really only if we start by tweaking the question a little bit. So specifically, I think we need to change the question from how do we become phenomenally aware, what neural and computational process are involved and how do they give rise to awareness. We need to start by taking a step back and instead ask, how can we study how phenomenal awareness is generated scientifically? So this is to ask, which are the practical approaches that are going to be most promising for giving us a handle on how phenomenology is generated? And which are the scientific approaches and theories that are attached to those approaches potentially, which make precise, falsifiable, unique, and quantitative predictions? And this is a really high bar. A lot of the theories that I put on the previous slide don't necessarily make predictions that fall into all of these categories. They might be precise, they might even be falsifiable, but there are an awful lot of theories that make kind of the same type of unique or non-unique qualitative predictions. So predictions like more quantum vibrations means more consciousness, or more information being broadcast means more consciousness, or information being broadcast at all means more consciousness, or more information in general, like information integration theory, that means more consciousness. These are not really satisfactory, at least not yet. That's not going to cut it. We're going to need to do better and try to make predictions from each of these competing theories that are unique, that are different from the predictions that the other theories make, that are quantitative and therefore can be falsified. And I think that the study of perceptual metacognition can help us do better like this. And in this talk, I'm going to try to convince you of the same, that no matter which theory you subscribe to, that perceptual metacognition provides us a really powerful handle on how to study consciousness scientifically. So before I launch into that argument, though, I want to make sure we're all on the same page about what I mean by perceptual metacognition. And so you've probably seen, if you've seen any of my other talks, this is a favorite slide, and so I apologize for repeating myself here, but I think it illustrates it really quite nicely. So this is the problem that your brain is faced with on every day, every waking moment of your life, is that you have these noisy, incomplete, imperfect sensory signals that are coming into your eyeballs. This is you have a brain, you have eyes, you're looking at this scene, and your brain's task is to decide what is the most likely identity of this thing that's out there in the world. And so your brain engages in an inference process that if you are Helmholtzian, you might agree is largely unconscious. So your brain says, okay, maybe this is a deer, or it's a car, or it's a tree, or it's one of those things. And so you decide based on some sort of computation that the most likely explanation for the information that you are receiving is that this is a car. And what comes along for free with this inference process is a feeling, a subjective experience of confidence. You either feel quite sure that you've made the right choice, or you feel not so sure and you feel like maybe you should gather more information. And so this is the target of what I want to talk about today, is how does the brain engage in these perceptual metacognitive judgments, judgments of certainty about a perceptual decision. And it's something that those of you who are studying human neuroscience and human psychology might be very interested in. But I also think that this is something that those of you who are studying artificial systems might be very interested in, because you kind of want your Tesla to be able to engage in these kinds of determinations too. You want your Tesla not to just to decide what it thinks it sees, but also how sure it feels and whether it should collect more information. So now that we've kind of introduced these ideas, you might be asking, well, why is metacognition a particularly powerful approach, particularly perceptual metacognition, a particularly powerful approach for trying to tackle consciousness? If what we want to understand is phenomenology, what makes metacognition special? And then I'm going to get into what I'm calling the metacognition as a step towards explaining phenomenology approach, and then we'll end with a summary. So first, why should we study metacognition at all? Well, I think that there are a number of practical properties that make metacognition a very attractive target, and they kind of have nothing to do with any of the theories that I showed you previously. Once again, it doesn't matter which of those theories you think is right. If any of them try to tackle how phenomenology is generated, then metacognition might be a useful tool for trying to test them. And this is because metacognition, or specifically here the outputs of metacognition as confidence judgments in a perceptual decision, metacognitive judgments are objectively definable. We can actually write down the computations, the equations that we think link some sort of property out there in the world, not only to a perceptual decision, but to a confidence judgment about that decision. We should write down what an ideal observer, a perfect system, ought to do in its metacognitive judgments, given the information it used to create the first order decisions themselves, like that is a car. And also, these objectively definable computations also have what I'm calling hierarchically dependent anchors. This means that these metacognitive computations are not only about an external reality and about an internal state, like your decision that that thing was a car, but they're also about the relationship between those two things. Your brain's job in coming up with a metacognitive assessment is to decide whether it is right, whether its decision matches external reality. And so what this means is that because metacognition is both quantitatively definable and has these hierarchically dependent anchors, we have a lot of power we can borrow from all of the models that have been developed to study perceptual decision-making over the many, many decades since, say, signal detection theory came out in the 50s. And so this is very, very attractive to us from a scientific and practical standpoint, because this gives our models of metacognition a lot of sensitivity and specificity. And I'm going to introduce here a graphical representation of what this means, just to give you a taste of this. So here is a stimulus that's out there in the world. This is like a probabilistic graphical model. Stimulus that's out there in the world, and then there's some function that maps stimulus onto internal representation, which we can write like this. And that internal representation takes as inputs the stimulus, but also maybe some other stuff like your attentional state, for example. So these inputs drive this internal representation, then we apply a decision policy and we get an estimate. That is a car and not a deer and not a tree. And then the metacognitive assessment kind of watches this whole system. So we have another arrow, another kind of generative process giving rise to an internal representation that is metacognitive, that is about The internal representation also takes these inputs potentially, and also about the relationship between this and this, which I'm denoting with this purple arrow. So this means that when we try to fit this system, we are trying to fit simultaneously this equation, and the relationship between the two. And I'll get into this a little bit more in a second. But of course, there are a lot of other things that might be described as objectively definable and having hierarchically dependent anchors. But metacognition also, as I mentioned, has something that it's like to feel sure. You get this qualitative experience, this visual sense of clarity. And so I think we can make the argument that studying the subjective sense of confidence makes metacognition at least sort of related to that hard problem of consciousness, the solution to the why is there something that it is like to be you. So I think that by studying metacognition, we can get at consciousness through these, what I'm calling 3 properties. And I'm putting them in a different order than I introduced them to you because that matches the order that they're listed in this preprint here. So if you want to go and read the preprint, this will help anchor you. So these are our theoretical foundations for why metacognition is special. It's that confidence has something that it's like, it is subjective, that metacognition requires or involves objectively definable computations. And specifically, and this is kind of the key one here, that metacognition involves these hierarchically dependent anchors. And this means that it's actually really hard to fit a metacognitive model to get all those moving pieces right, because there's a lot of interdependence. And so you tweak one piece of the system and the rest of it kind of falls apart. And this is actually really good from a scientific standpoint because it makes it hard to fit the models, which means that if you get your model to fit, then maybe you've discovered something really true. So the argument is essentially that metacognition is going to give us unprecedented precision of inquiry into at least one type of phenomenology, the feeling of confidence. And this is precision that's unavailable for type 1 models alone, models of just the decision, just that is a car. That you don't get this level of precision because of these hierarchically dependent anchors. So this is what I'm calling the M-step approach, metacognition as a step towards explaining phenomenology. And so I thought then what I would do is explain to you what this approach is going to look like from a practical perspective in the hopes that I will convince you to join me in studying consciousness with metacognition. Okay, so how do we do this? This brief primer is probably unnecessary for this crowd, but I wanted to go through it anyway to make sure, again, that we're all on the same page. So if you're fitting a model of any kind, not just a Monte Carlo simulation computational model, any model from linear regression on up, you have a model, you make predictions with your model, and then you want to compare your model's predictions to empirical data that you have observed out there in the world. And the degree to which your model predictions fit your empirical data can be quantified with a goodness of fit measure like an R-squared value in your regression model. Can you predict Y from X, and how well can you predict Y from X? That's a goodness of fit measure. So in models of these perceptual decision-making and confidence judgments, the likelihood function, which is a measure of the goodness of fit, looks something like this, where we take the model's predictions, the probability of giving a particular response, having seen a particular stimulus from the model, given certain parameters, phi, and then we compare that to the number of responses given by a person in each probable category of responses, given that they saw a particular stimulus. And so when we do model fitting, what we like to do is we want to vary phi, which is a vector of parameters that the model takes. And we want to find the best fitting parameters that maximize the likelihood of the model with those given parameters, given the data that we have, the data, which is this empirical data here. And so ideally what will happen is your model will be well behaved and you'll be able to do maximum likelihood estimation and say, okay, I found the best fitting parameters. This is the best set of parameters to fit the data that I'm seeing. But of course, this doesn't mean that you've got the best model. There might be a model out there that's just overall better and that overall produces a much higher likelihood of the model given the data. And so just because you found best fitting parameters doesn't mean you found the best fitting model. But the nice thing about this is that then you can do formal model comparisons, and you can say, okay, given the number of parameters that I have, which is the better model, et cetera, et cetera. And since this is not a statistics class, this is about as far as I'm going to go here. But again, keep this in mind. So then you're probably thinking, okay, model fitting, that's not specific to metacognition here. Why do we care about metacognition again? We could just do model fitting. We could make predictions about, making decisions about, do I see a face or a house, or do I see a car or a tree? Why do we need metacognition in the equation? Isn't this just model fitting, like what everybody else has said for decades and centuries of statistics? So what I want to remind you of, again, is property 3, which is that sensitivity and specificity that we get from the hierarchically dependent anchors. And again, this is because it's really, really easy to break a model of metacognition. It's really hard to get it to fit right. If I change this piece, then that, by definition, changes the relationship between this piece and this piece. And so it's like you kind of have all of these balls in the air, and you have to juggle them all at once in order to fit the model correctly. And so essentially what this means is that it's easier to break these hierarchically dependent models that have hierarchically dependent anchors. Anchors being ways to compare them to the outside world, to the data that you have. So in a hierarchically dependent model like this, you can compare your model's predictions to the data that you have, both at the type 1 level, so this is deer, car, or tree, and at the type 2 level, which is having decided that it's a deer, but it was actually a car, should I feel high or low confidence? Having decided that it's a car and it's actually a car, should I feel high or low confidence, and how confident should I feel, and so on. So when you look at kind of these, sorry, this is a busy slide here, but it just kind of serves to drive home the statement that if I have a stimulus that's out there in the world that can take on one of 2 identities, and then I make one or two of 2 responses, or I have 3 identities for the stimulus and I have 3 possible response categories, I'm going to produce, I as a human, am going to produce a distribution of responses that fits into either 4 or 9 kind of little boxes. But if I add metacognition, now this gets a whole lot more complicated. So if it actually was stimulus 1, and I said stimulus 1, but I'm correct, so I'm correct, but I say low confidence, then this is what's called a type 2 miss. And the only way to get the proportion of type 2 hits, misses, and so on correct is to actually model this whole system. You can't just model the top half, or you can't just model the bottom half. You have to get the whole thing right. So it's really easy to break this and to have the models diverge from the data to show that one model is potentially better than another one. So I wanted to share with you a little bit of the work that we've been doing in my group, showing how this actually works and the types of experiments that we use to study the experience of confidence with these computational models. So I'm going to go through a couple kind of psychophysics and brain stimulation papers. We're going to skip these, just go through them really quickly, and then we're going to go through some ongoing work as well. And all the citations for these papers are at the bottom. So if you find this intriguing, you can please go have a look and look them up and send me an email if you want. Okay, so this paper here was an example of us trying to understand how blind sight-like behavior can be created in neurotypical observers, not people who have actual neurological disease or injury. So blind sight is a neurological condition in which damage or disease in primary visual cortical areas at the back of your head leads to a condition where you can identify visual stimuli above chance. So I stick a thing in front of your face and say, what is this thing? And you can tell me above chance what that thing is. But then when I ask you how confident you feel, or I ask you whether you saw something at all, you say, no, I saw nothing. So blind sight is very intriguing from a scientific perspective because it gives us the opportunity to study the type 1 behavior separate from the type 2 behavior. So that means maybe you can tell deer, car, or tree just fine, but you feel like you can't see it all. So it dissociates the top half of that graph that I showed you here. It dissociates this half from this half. So blind sight is, of course, very rare. There's only a few patients worldwide that have true blind sight. And as much as we could potentially create it in monkeys, let's not do that if we don't have to. Let's study it in neurologically intact college students if we can. And so the prevailing wisdom has been, let's show you a stimulus on the screen, and let's ask you to discriminate it, and then ask you whether you saw it. And if I use, say, forward-backward masking, then you might say, oh, I didn't see anything, but still be able to do the task. But we weren't satisfied with that, because just because you said you didn't see a thing doesn't mean you had actually zero experience of it. So we wanted to study with psychophysics and computational models how a system ought to behave under ideal circumstances. So we changed the paradigm a little bit. We show you in a psychophysics experiment, we show you a target on the screen. This is a Gabor patch here that's like a sinusoidal grating tilted left or right from vertical. And we showed you a thing and asked you to say, is it left or right, tilted left or right from vertical? We show you another thing and ask you to say, is it tilted left or right from vertical? But here we were kind of sneaky and we actually removed the target. So I show you a thing, I ask you to discriminate it. I show you nothing and I ask you to discriminate it. And then I ask you to bet on which of these two decisions you think you are more likely to get right, that you feel more confident in. And the idea here is that because this thing is actually physically not there, that we're setting a floor on confidence. So we're asking, if you can discriminate this thing above chance, do you have the capacity to rate some sort of confidence in your choices? Or is it the case that we've created blind sight-like behavior? And to test what an ideal observer computational model would do under these circumstances, we built a model that looked like this. So this is a graphical representation. These are meant to be generative hills of noisy samples. So this is like a two-dimensional Gaussian kind of hill of probability as viewed from above. And we draw a sample from either the left tilted thing or the right tilted thing, and we categorize it as left or right tilted based on how close it is to each of these two circles. So this sample would be categorized as left because it's closer to the left generative distribution than the right generative distribution. And then we also can say how much closer is it to the left thing than the right thing, and that gives us a confidence judgment. So mathematically, what's happening is that we draw this sample and we're calculating the posterior probability of this distribution or that distribution, and then the confidence is exactly that posterior probability of the choice that you made. And then for the target absent condition, we draw another sample, this time from the noise distribution. We go through the same exercise, we get a choice and a confidence judgment, and then we compare the posterior probabilities of these two things and say which of these two things are you going to bet on. And the model produces predictions that look like this. So as the contrast of this target climbs and the task gets easier and easier, the model does better and better, and it also has better and better ability to bet on that target present interval, to say that one seemed more confident. And if you're wondering why this is not just like rising along the identity line here, it's because this orientation percent correct in the target present interval depends on a single sample from the target present interval. And this y-axis depends on a comparison between this interval and this one. So it kind of dips below the identity line there. And just to drive home again, the difference between a type 1 task only, just left, right, left, right, left, right, versus left and high confidence, right and low confidence, left and then right, and then I'm going to bet on one of these and so on. If I just had left and right decisions, just the objective identity of the target, then I would only have a few responses that look like this to fit between the person's data and the model's data. So this is not a very detailed, not a very rich representation on which to compare my model and my data. If I add confidence into the mix, it gets a lot bigger. And remember that not only did it get bigger, more points to fit, but it also means that those points are interdependent with each other in a very complicated way. So the distribution that generates this overall response distribution, the model that generates this overall response distribution needs to get every single piece of that hierarchical structure right in order to accurately produce these categories of responses. So the results of this project are that this was our model. We had a blindside observer that we compared it to. This is kind of what everybody in the literature expected to have happen. The blindside observer would kind of do the task above chance, but then have no ability to bet on its choices until it kind of reached a conscious threshold. These were our data that we got from our human observers. We did 2 experiments. They look a lot more like this than they look like this. We did a couple more experiments. Again, they look a lot more like this than they look like this. And so we can actually quantify how well the model fits the data and say, we think that the humans are producing ideal observer behavior. That this mathematical description is an accurate description of how the human's information processing is occurring. Now you might say, okay, great, that's lovely. You had one model that was an ideal observer, and then you had this kind of stupid blindside observer that nobody really expected to have happen, although that's a conversation for another time. But these are the only 2 things that you were comparing, really? Like, come on, there's got to be other options. So, of course, we decided let's do it again and let's use a different masking technique. In this case, we're not actually using visual masking at all. We're using transcranial magnetic stimulation. So same idea, show you a thing, zap you in the back of the head, which makes it harder for you to do the task. It injects a huge amount of noise into your visual cortex. And then show you nothing and don't zap you. But of course, counterbalance whether we zap you or don't zap you when the target is present and absent, so you don't kind of catch on to our trickery. And then we say, which of these things are you going to bet on? And then we built the ideal observer again, and then we saw something kind of disappointing and awful, which is the black line is now the ideal observer's behavior. We add noise to the model. We let the model estimate the noise as it's supposed to be able to because it's doing metacognition. And so it knows that the noise has gone up, and it reduces its predicted performance and reduces its predicted confidence as a function of the reduction in performance. If I'm doing worse on the task, I ought to feel less confident. So this is what the model predicts. And this big red arrow here shows how far off the model is from the humans, which are the red guys. So the red line is the humans, the black line is the model, and now we're in trouble because the ideal observer no longer even qualitatively predicts what the humans are doing. So then we thought, okay, we better build some more models and see if we can come up with an explanation for what's going on here. So we built what we called a heuristic observer model. And the only difference between these 2 models is that the ideal observer is allowed to estimate its own noise, and the heuristic observer is not. The heuristic observer is supposed to just use the noise that you told it to use, never mind what the actual noise was in the system. But now the heuristic observer actually matches the human behavior. So that's interesting. This suggests that this model, this set of equations, is a better description for how people are engaging in metacognitive computations. So now our ideal observer model is out, and this guy appears to be the winner. Well, okay, we better do some more experiments to see if we're right. So now we did an electrochordatography study, show you a face or a house and ask you to discriminate it. Is it a face or a house? And then rate your confidence in it. And we do this in patients while they have electrodes physically sitting on their brains, taken off the top of their head for the purposes of epilepsy surgery. And while they're sitting in the hospital, we stick these electrodes on their brains and we ask them to look at faces and houses and press buttons. And then we did some decoding. So we did some very basic machine learning here. We take the output of the decoders, which we can think of as kind of the cleaned data that we extract from the brain, and we feed it into our models. And now here we've got another model that we developed on the basis of some previous work. And we thought this was a better shot or a better potential fit than the heuristic model from the previous work. And now this guy is winning. So once again, the ideal observer is a massive loser, and this heuristic model is winning. So now we have yet another candidate that we're going to have to arbitrate between. So we figured, though, first we better see whether this particular model is implementable in neurally plausible architecture. The idea there is that the brain doesn't have equations, the brain has neurons. And so if we think that this is the winning model, we better believe that this is the type of computation that can be actually instantiated by neurons. So we built this neural network model, and yes, it does. So this is another study that I'm not going to go into in detail, but I just want to point out that there's this very there's a unique crossover between the blue and the red. They kind of go like this. That's really hard for most models to fit. This model crashes and burns when trying to fit this data. But we built this neural network model that kind of instantiates this model here, and you see a nice match between the dotted red line and the solid red line, and so on. Okay, so what this really highlighted to us is that it's really hard to fit these models. It's really hard to get them right. It's really hard to come up with one that makes unique predictions because they all kind of seem to break in similar ways. So what we really need to be doing is ignoring the bottom half of this graph altogether and try to just focus on the top half for now. And we need to cut this model in half. And the best way to do that is to not worry too much about how the stimulus gives rise to decisions, but just say, okay, having measured the decisions and the decisional capacity, can I just get at the confidence judgments? Can I get this function right? And then we'll kind of build our way back down. So what this means is that we need to, what we call, clamp the type 1 performance. We need to make you make exactly the same type 1 decisions. You say deer, 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 car, 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 tree, 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 no matter what your confidence judgments are. And then we need to find a way to bifurcate, to separate those type 1 decisions from the confidence judgments, such that we can create conditions where you say, where you're just as correct or incorrect in the task, but in one condition you feel more confident than you do in another condition. So here on the x-axis is d prime. This is a measure of performance. You can think of it like % correct. And then on the y-axis we have confidence. So again, we create conditions where everything on the bottom half of that graph is matched, and all we're trying to mess around with is the inputs and the computations that give rise to the feeling of confidence. And we could do this not just at one level of d prime, but maybe at 2 levels of d prime. And so that would be nice. And this is what's actually been done in the past. You create conditions where d prime is matched, but confidence differs. And the hope is that then you are trying to push around on just the confidence, then you haven't actually touched any information processing. I'm just going to go back really quick. You haven't touched this purple arrow and you haven't touched the red thing. You've only touched the blue thing. So that's very challenging. But a lot of these rely on the supposition that you have actually matched d prime. And the problem there is that just because you fail to find a significant difference in d prime between the black thing and the red thing does not mean that d prime didn't actually change. It just means you failed to find a significant difference. So you have a failure to reject the null hypothesis instead of just like a proof that the null hypothesis is true. So what we'd like to do is actually characterize this whole function, the relationship between performance and confidence across a whole range of conditions, a whole range of performance levels, a whole range of stimulus manipulations, and so on. And we want to find the stimulus manipulations that maximize the difference between this red line and the black line so that we kind of take confidence completely out of the equation. And then we can just characterize this whole function and never mind about matching d prime. And so what this means is that we're trying to focus not on building the relationship between the stimulus and the perceptual decision, which we all know is called a psychometric function, but between the perception and the awareness or the confidence judgment, which we're calling the type 2 psychometric function or the meta-perceptual function. So in this study, which was completed by Brown, Maniscalco, and Olenka, Olenka was actually an undergrad when she did this study, so I want to highlight that because it's particularly impressive. So here we show you a field full of moving dots, kind of looks like a little snowstorm on your screen. And then for half a second on one side of the screen, those little snowstorm dots move coherently in a little waterfall, just like down. And we can control the difficulty of the task by setting the percentage of the dots that moves coherently downward in the little waterfall. And then they go back to moving randomly again. And your task is to say which side was the little waterfall of dots on and rate your confidence. And we manipulate confidence separate from performance because, well, we can set the coherence, the kind of number of dots or percentage of dots that are moving coherently downward instead of all randomly. We can also set the overall number of dots on the screen. So this is what we're calling dot density, and we can create conditions where this little snowstorm looks kind of like flurries. So low density, just a few dots kind of moving around on the screen. And then we can also create conditions where this little snowstorm looks like a blizzard. So that's this high density condition. So there's a ton of dots on the screen. And we want to see whether putting the snowstorm all together, like low density flurries and high density blizzard, whether we present a bunch of trials in a row that have the same density, or we fully interleave the trials, which one creates a bigger bifurcation, a bigger separation between performance and confidence, because that will allow us to best characterize that relationship. So the blocked design, which is this one, looks like this, not a whole lot of difference. D prime, confidence as before, and all of these lines are basically overlapping. But the interleaved condition actually looks a lot more promising. We've got nice separation here between performance and confidence in a way that demonstrates that the interleaved design actually might allow us to characterize this whole relationship, to build models to try to fit this. And we can test those models by saying, do they produce higher differences between performance and confidence at these higher D prime levels? And do they characterize the difference between performance and confidence from the model side as a horizontal, not a vertical shift in this meta-perceptual function? So we're looking for cases where the function shifts left and right, not up and down. And if we can build a model that does that, then that's great. That means that maybe that model is a strong candidate for the relationship between performance and confidence, and kind of building that whole causal chain from stimulus through response through confidence. And the last study that I'm going to mention today, and then we'll have a little bit of time for discussion here, is this one. And so this is another candidate for how we might separate performance and confidence using these matched performance, different confidence or consciousness kinds of effects. And this comes from the observation that you might remember from your high school biology class or freshman neuroscience class, that the center of your visual field has more cones. And so it has higher spatial acuity. And what this results in is that when you look at something and you put it in the center of your visual field, you're going to do better at a task, and you're going to feel more confident in your visual choices. And the periphery is the opposite. You don't have a lot of cones out there. You just have a lot of rods and a few cones kind of scattered. And we have lower spatial acuity and therefore lower confidence. But there's an interesting observation here, which is that even though the center has higher spatial acuity, and the peripheral vision has lower spatial acuity, we feel like we can see pretty well in the periphery. We don't feel like the periphery is this blurry black and white blobby thing, and the only color vision and the only precise vision that we have is in the center. This is not our experience. This one is. If you just sit right now in your home office or your bedroom or wherever you are, and you kind of attend to your visual periphery, it really kind of doesn't look like this, does it? It looks like this. And so this is kind of a conundrum, because we know that the information that's coming from your visual periphery actually is this information, but subjectively, your confidence experience of what you're seeing is this one. So we set about trying to figure out how this might occur computationally. And we took as a cue a history lesson from natural scene statistics. So in the early 2000s, and a little bit earlier, actually, so I'd say late 90s through maybe 2010, 2011, there was this really big push for natural scene statistics and how they impact our visual perception in particular. So here's an example that we have learned through our experience that light typically comes from above. And so we see this one as bumps, and this one as little dimples going into the screen. And we know that this expectation can be changed, which means that we've learned it through experience. We also know that when people are making orientation judgments, so I show you a line and ask you to categorize if it's like vertical or horizontal or oblique, or which one is more vertical than another one, that the orientation judgments that we produce demonstrate that we have an expectation that vertical and horizontal orientations are more prevalent in our visual experiences. And this is one that you can test right now, and this one too. So check out where light is coming from in your world right now. It's probably more likely to be coming from above than below. And just take a look around you and see that vertical and horizontal lines or edges are more prevalent than oblique ones. You can look at, like, you know, the windowsill and your computer screen and your door frame and the trees outside and so on. And people are sensitive to this, and it drives their perceptions. And so we thought, well, what if the metacognitive system has developed expectations about noise? Specifically, what if the metacognitive system has learned that the center of your visual field tends to be less noisy, and the periphery of your visual field tends to be more noisy? And an additional supposition is that in the periphery, the distribution of noise that your system experiences is likely to be positively skewed. And this is kind of a default assumption because noise can't be negative. And so if it's going to be bigger, it might as well be positively skewed like this. This is true for kind of distributions of size and weight and so on that cannot be defined negatively, that positively skewed probability distributions are a great way of describing them. So if this is the true distribution of noise that you experience in the center of your visual field, and this is the distribution of noise that you truly experience in your visual periphery, we thought, well, what if the system makes one mistake in its estimate of what types of noise to expect in the visual periphery? If the visual periphery, if the system, the metacognitive system, assumes that the distribution of noise in the visual periphery is bigger than in the center, but still normally distributed around some most likely noise level, and this is the only mistake that it makes, and then it estimates noise in a perfect Bayesian way. It takes the prior expectation of noise and the incoming information, and it puts them together to estimate noise, but it makes the mistake that it gets the prior wrong. Can that explain visual inflation in the periphery, this over experience of confidence in the visual periphery? So we built a model that does this, and then we built some other models that kind of come from the literature. And I'm not going to go into the details right now, but I'm going to tell you that two of these models are kind of perfect. They have optimal, perfect access to noise. So that's like in the TMS study back earlier in the talk, that these are the ideal observer models. And then we also built a blind model. So that's kind of like the other model in the TMS study that I told you previously. And then we also built these kind of two different types of imperfect models. And one of them is this one, that it gets everything perfect. It's perfect in every way, except that it makes the mistake about the expected distribution of noise in the visual periphery. And then we calculated under a bunch of different simulated conditions what the performance and confidence of these observers ought to be. And you can see that the perfect observers, which are the green guys here, performance and confidence always matches. Performance and confidence always matches, both in the center and in the periphery. We get a little underconfidence on this one and a lot of overconfidence in the visual periphery for this fully blind model. But then we also have these other imperfect models, and they're doing a great job in the center, but in the visual periphery, they're predicting inflation, overconfidence relative to performance in different magnitudes and in different ways. And so now we have a way that we can say, oh, well, maybe these are the models, either the blind or these imperfect models, maybe these are the ones that are actually a good description of how confidence is generated. And the last thing I'll say here is that this pattern does change under attentional manipulations. So peripheral inflation gets weaker when attention increases. So we found a study that showed that under inattention, performance drops, and confidence in correct trials does not change, and confidence in incorrect trials actually increases when you have unattended conditions. So performance dropped and confidence in incorrect trials increased. So we simulated a bunch of conditions with these models, and we looked for cases where confidence in the correct trials did not change, and confidence in the incorrect trials increased from attended to unattended. So if we do attended minus unattended, we're looking for a negative number, 0 and a negative number. And the only model that did this was model 5. So you can see under all of the conditions we simulated, confidence in the correct condition does not change. Confidence in the incorrect condition follows this pattern, and none of the other ones did that. So this suggests that this model, in particular, this specific way of imperfect expectation about noise, is a good description for how the system is actually doing estimation of confidence in the periphery. Okay, so that's the kind of bulk of the talk here. Just in the last 2 minutes now, I want to go through kind of what we'll get, because we started talking about confidence, we started talking about consciousness, and then I forced you to think about confidence for a long time. And you might be thinking, okay, wait, I really want to study consciousness. I really want to do that. So this is more than just model comparison between a few competing models. This will give us the language to separately study inputs, functional forms, characterizing the distributions, decision policies, and closing the feedback loop. And I want to preface this by saying there's a lot of really good work right now on this, but all these pieces are kind of largely jumbled up. So, for example, if we want to factorize the inputs to G, this function here, we're basically saying what causally influences confidence, and therefore causally influences the feeling of confidence. And here's a whole bunch of candidates that have been shown to actually causally influence confidence, but we don't know why or how they interact. We also want to explore the functional form of G. So we can say, is this a normal distribution that just kind of reads out this and adds some noise? Or are there other things at play? Do we have compression? Do we have factorization? Do we want to compute some statistics about this distribution and feed that in here? Is that what this is doing? And so on. We want to characterize the distribution of Y, which is the second order representation. What are its dimensions? Does it share dimensions with X or not? What is its temporal resolution or evolution, and so on? We want to study the decision policy for Y hat. Maybe we characterize this whole system perfectly, but we change the decision policy a little bit. So is this the maximum a posteriori estimate? Is this the mean? Are they always the same? Can you change the decision policy? And finally, we know that this is not a one-way system, that stuff up here can also influence what's going on down here. And so I think if we really dig into this, we will get unprecedented precision of inquiry about phenomenology, because there is something that it's like to feel sure. But we've got a lot of work to do. All of these steps are jumbled up right now. Okay. So when we want to answer the question of how we become conscious, to arbitrate among all of these possible theories and more, I hope I've convinced you that metacognition gives us a really precise language to do this. Because of the three properties that I described, that it's subjective, that it has objectively definable computations, and that it has these hierarchically dependent anchors, and it's a hard system to fit. And I think that by studying metacognition, we will be able to start building generative explanations instead of causal explanations. So Lisa Meraki is one of my favorite philosophers, and she very succinctly describes this as saying, causal explanations help us understand how events unfold through time, but it is generative explanations that help us understand how new kinds with distinctive causal profiles and other explanatory properties emerge out of the organization of other objects and properties. And so I think that metacognition is going to help us start to build those generative explanations, to understand not just what influences conscious experience, but also how that occurs. So I think, yes, consciousness can be studied scientifically. Metacognition is going to help us get there. But we, of course, have a lot of work to do. And so if I've convinced you of this argument, that means I also want you to join this cause. And so I know that this is a Canadian symposium, but a few of you might be here in the United States or thinking about moving to the United States. And I mention this because we have some money from the Templeton World Charity Foundation. For those of you who are about to graduate with your PhDs, you will become eligible for this. Postdocs and early career faculty even. We've got about $150,000 US to give out in sub-awards for people who want to study consciousness scientifically. So if you're interested, help spread the word and help us solve this problem. And that is it. Thank you all for your attention.
Thanks, Megan. That was amazing. Thanks a lot for the great talk. I think we are very, very fortunate to hear you talk about such a recent preprint and have an overview of multiple experiments the last few years. So yeah, people are clapping now in the chat. I think we had some issues with the chat before.
Yeah, I saw that.
Anyway, it's working now. We don't have a lot of time for questions, but we have a couple here.
Great.
So we have one by someone in our team because it's logged in as unique. So I'm going to read that one. And then we have a question by Charlotte who will ask it on screen. So maybe Marie-Ève, you can bring her on screen. And in the meantime, I'll read this question. The first question is, how do we take into account the real-time feedback loop of information coming from our senses in this kind of model once a decision is made or the level of confidence has been established?
I think this is a beautiful question, and it's absolutely right. Like, this is not a static thing. You don't like see a single sample and then make a decision and then you're done. This is a continuous, ongoing process, and we know that the decisions that we make and the confidence we have about those decisions actually changes the way incoming information is processed. So Toby Donner's group has some really beautiful work on this as well, not with confidence necessarily, just with decisions. But I think that the answer is that we can describe all of this computationally and mathematically. So the entire system that I just specified, you can make that all a function of time. And then you can make the inputs be a function of like whatever happened at time t-1 or whatever. And so I think that this is a perfect way of thinking about this, because you can then link it to evolving neural activity patterns. You can link it to evolving decisions that are sequential, that happen like one after each other in time. So the answer is that this is just totally cyclical. There's not like, you make a decision and then like you kind of move on with your life. It's that decision that you make at time t becomes the input or changes the incoming information structure for whatever is happening at time t+1.
Cool. Charlotte, go ahead.
Yes, thank you. So I actually have two questions, but I only put one in the chat, so I will start with this one because it was upvoted, so other people might be interested in this. So the question is, the models that you have shown were really interesting, and I was interested whether there were individual difference in the prediction of this model, like for different participants, whether there are some participants which are like more model-like, which behave more like the model prediction. Is there research on this, or is it only analyzed on group level? And yes, that's the question.
Also a fantastic question, and thank you for asking it. In some of, I can't give you details because I don't remember the individual difference details from some of these studies, but there are individual differences. Unfortunately, a lot of these studies, the cohort is too small to effectively study individual differences. But one of the things that I think is powerful about studying metacognition and consciousness with these computational approaches is that if you get a big enough cohort, you really can do that. And I know that you can do that because we see it done with computational models of perceptual decisions. So there's a lot of really great work from Brian Odegaard when he was a PhD student and a postdoc doing multisensory integration work. And Brian was my compatriot, and he ran, I think, like 300 people through every single study that he did. I mean, he just lived in his like experimental running room. And they did a lot of these individual difference things where they said, oh, this decision, the system is the same, the generative structure is the same, but the decision policy is different from person A to person B. And so you can show that some people are really fit better by one decision policy, even though the rest of the generative model is the same. But we need that precision of language to answer those questions. And I don't know of a lot of studies that have done that in metacognition yet.
Okay, thank you. Thank you for your answer, and thank you for this great talk. Do we have time for the second question?
Go ahead. Quick question, quick answer.
Thank you. Yes, it's because you have mentioned so many different theories of consciousness on your slides. And from my experience, I have seen that global workspace theory, for example, has published quite some work on visual stimuli and when it becomes conscious. Would you argue that your models fit more to some theories of consciousness than others, or do you see your research as a validation for one of these theories?
Also a great question, and I will try to go quick in my answer. So I'm trying to think about this as a way that is trying to be theoretically agnostic, to say what are the tools and techniques that we need to focus on to make progress. But if you push me, I will answer that metacognition is a decision about a decision or a monitoring of an internal process. And so that sounds an awful lot like higher order theories. So I think that higher order theories in particular are suited to this type of approach, but there's nothing saying that global workspace couldn't be made up of a bunch of higher order representations instead of a bunch of first order information. So Axel Clearmans has this recent paper from 2019 in TICS showing that the global workspace can be made up of a bunch of higher order representations. And so this is, I think, where, and there was a recent paper like the global workspace needs metacognition. And so I think that there are ways that we can bring together some of these theories to show that maybe they're just two sides of the same coin, or finding cases where, no, they really disagree. And those are the points that we need to put pressure on.
Thank you very much. I totally agree on this.
Great. We have another question by Karim, but I would say that in the interest of time, because we're going to have another chance later on the panel, I think this would be a great question for the panel. And it's also a great way to let everybody know that in about 15 minutes. Oh, here we have Karim. Would you be available to ask the question later on the panel, Karim?
Yep.
Would be great, because we're going to have the active break in 2 minutes. So great, thank you. So yeah, I just want to thank again Megan for her talk, and for everybody else, thank you for being there as well for the questions. And in 10 minutes or so, we're going to be in the panel session, in the panel discussion with Megan herself, Pim, and Stephanie Blaine-Moraes and Irina Rich. I can't wait for this. I think it's going to be great. So yeah, see you in a bit.